Hello, good afternoon, and welcome to the webinar today. I'm very happy that you could attend. And of course, the first item on the agenda is if you can mute yourself while the webinar is going on, and it'll be open for all. If you want to ask questions at the end, you can unmute yourself and ask the questions. As far as I just wanted to quickly go through our website. It's called wcsawma.org. That's our main page. If you go to the events page, or you can click directly, it'll take you to this webinar that we're going to have right now. But I wanted to show you, if you go into our previous meetings, the previous webinars are here also. And what we do is we upload the presentation and the video from the webinar on this page. If you want to access that, you have to go through the previous meeting tab, and any of the webinar like we had in February, Dr. Ramanathan. And this presentation video and the complete presentation everything is here. So for the current webinar, today's webinar, that's where we'll be uploading after the webinar in the next couple of days. We'll have video and the presentation right here if you want to access those. Do visit our website. There are a lot of new things that we keep adding. We've added some jobs that have currently come up here also. So do check it out. And with that, I'll hand it over to Bernadette for an introduction. So Bernadette, it's all yours.
Thanks, Bhaskar. I want to welcome everyone to our webinar today. It's using remote sensing to detect, validation, and quantify methane emissions from California solid waste operations. Our presenter today is Dr. Daniel Cusworth. Dan Cusworth is a research scientist at the University of Arizona and project scientist for carbon mapping. He was formerly a data scientist at NASA Jet Propulsion Laboratory and worked on quantification of anthropogenic carbon dioxide and methane emissions from regional to facility scales. His main research interest is to design multi-tiered observing and analysis frameworks where multiple atmospheric carbon observations are jointly assimilated to provide actionable data for greenhouse gas emission mitigation. He received his BS in Applied Math Atmospheric Sciences at UCLA and PhD in Atmospheric Chemistry at Harvard University. I think its topic is very timely as we're starting to hear about all kinds of new requirements for methane and carbon dioxide. So we look forward to hearing your presentation. Daniel, take it away.
Okay, great. Thank you so much. This is really an honor to be able to talk to you today and share some of the research that I did that we're doing right now, but also started when I was a data scientist at NASA Jet Propulsion Laboratory, and some of the instrumentation and approaches that can be leveraged for quantification of landfill methane emissions, but really the entire greenhouse gas sector generally. So a lot today I'm focusing on landfills and composting, but this type of measurement system is also applicable for the entire greenhouse gas sector, from coal-fired power plants to methane emissions from oil and gas infrastructure to dairies and livestock emissions. And so the real idea of this is, how do we leverage top-down information in addition to what we're getting from bottom-up process models? How do we leverage something from the top down, from the atmosphere? What is the atmosphere actually telling us about these types of emissions? And what can we do with these types of observations? We can use them for reporting. We can also use them for mitigation. We can use them to understand the landscape of facilities. But it takes some thought, and it's as soon as you have some new type of instrumentation possibility, it opens up a can of worms. But it's a good can of worms, and these are the types of questions we need to be asking and implementing as we try to reduce greenhouse gas emissions locally and eventually globally. So just focusing on the first today we're talking about landfills, and I wanted to back this up or motivate this at least by talking about emission quantification generally from landfills. How do we do that? How do we do that systematically? So I'm sure everyone has lots of different approaches. There's several different types of models. I'm going to focus on one in particular, the LandGEM model, which is used widely by US EPA. It's a bottom-up process model that uses waste in place and assumes some decay coefficient, which I have kind of in this equation here, what the methane generation capacity is, the waste that's incoming, and then that gives you a methane generation rate. If you assume a certain amount of that is oxidized and a certain amount of that is captured, you then ultimately get an emission rate. And so this is generally the backbone of how emissions reporting happens, at least federally, to EPA. And when we're making inventories nationally of saying what is the contribution of the waste sector to the national methane budget, how does that compare? It's basically this type of modeling that is used to underpin those types of estimates. So, EPA reports about 20% of the anthropogenic methane budget comes from waste. So that includes, landfill, wastewater, and composting. And most of that is from landfill, and most of it is with this type of emission estimate. And, probably broadly speaking, this does generally represent what's going on. But if you look at this plot I have, this correlation, it's basically the emission estimates are very strongly correlated with waste in place, right? The amount of waste that's coming into the landfill. And so that's good, but obviously, as many of you on this call know, that's not the entire story, right? What's happening in terms of the operations? What's happening in terms of the composition of the waste? How is that waste being treated? How old is the landfill? Is there construction happening on the landfill? How many wells are in the gas capture system? How much are they processing? I'm getting a little bit of feedback here. I don't know, we might need to get some microphones muted. But anyway, so that's the question. And so what can top-down measurements tell us about it? And so I'm going to get a little bit technical for a second and introduce a technology called imaging spectroscopy. And before I even talk about imaging spectroscopy, I want to talk a little bit about remote sensing of methane, of greenhouse gases. So methane and carbon dioxide, but we're talking about methane today, is a greenhouse gas. So what that means, we know that heats the atmosphere, but what is that? What's actually happening? Well, what it means is that there are wavelengths in the, in the solar and thermal spectrum, radiation that comes down from the sun as it penetrates through the atmosphere and reaches the surface. Methane is a greenhouse gas, so it absorbs some of that radiation. And because it absorbs that radiation, that energy stays in the earth. This is a real crass approximation. That energy stays in the earth as opposed to getting scattered off and going back out to space. And so we heat up the earth, right? So that's a real, broad strokes greenhouse effect. But so there's certain wavelengths in the infrared spectrum where methane absorbs this radiation. So if you know where that is, and we know where that is, what those wavelengths are, and you design an instrument that is sensitive to those wavelengths. So you think of your digital camera being, RGB, red, green, blue channels. Well, if you develop an infrared camera that is sensitive to the wavelengths where methane absorbs solar radiation, well, then you can infer what the concentration of methane is in the atmosphere. And that's the backbone of remote sensing. And so satellites do this, airborne instruments do this, and the one I'm going to be talking about extensively today called the AVIRIS-NG. So this is the Airborne Visible Infrared Imaging Spectrometer, Next Generation. It's kind of a mouthful. Does exactly this. It flies along the Earth's surface, and it senses solar backscattered radiation in the wavelengths that methane and CO2 and other gases absorb. And it does this at very fine spatial resolution. So it produces maps that are of about a 3-meter spatial resolution. So you can really pinpoint where point sources are, or you can really see, if it's in the visible channels, really see what's underneath you. So I'll get back to that in a second and show how we leverage it. But first, I also want to talk a little bit about what a remote sensing technology is sensitive to when we talk about emissions. And for that, I want to decouple emissions that we might expect to see at a landfill. And again, this is an approximation, this is a simplification, but it's illustrative of when we're trying to think, what does remote sensing do and what does it not do? So here's just an example of a landfill. And I've drawn little flux arrows around here to represent one of two things. The orange arrows are small, and they represent what I would call an area emission. So this is a diffuse emission. So pretty much anywhere on the face of a landfill where you have some buried trash somewhere, you can probably expect some small, could be negligible, but some small emission of methane permeating from the surface. And so this is going to happen all over the face of the landfill. It'll be diffuse, it'll be small, but in aggregate, it might make up a significant emission source. Now that's in contrast to another type of emission, which I'm going to call a point source emission. So this will be a very discrete single place on the face of a landfill, or a few places on the landfill, where you might have a just anomalously large emission rate relative to the rest of the emissions. And so this could be, let's say you have a well in your gas capture system that's broken, that got flooded, and so it's just venting methane. So this is a strong point source that's going to be, much larger than all of the smaller diffuse sources, and might make up a large fraction of the total emissions on the face of a landfill. So thinking of it that way, a diffuse area source versus a large point source, remote sensing is really good at the point sources. It doesn't address the area sources. So the emissions I'm going to be showing you today, what we're talking about are things like construction or leaks or something that's problematic, or an uncovering of some trash, something that really produces a strong emission rate. But what's interesting about this is that these are generally types of process level emissions that might not be captured in bottom-up inventories as well. So not only is it a different type of emission, it's something that maybe is not captured in a bottom-up inventory, but that might be indicative of an issue that you have on your landfill, and could actually be a very large contributor to the total emission coming from the landfill, as much as 50% or more. Okay, so here's just an example of what I mean. So here's a landfill in Northern California that we flew with our airborne instrument, and the RGB channels. Google Earth is on the left, and on the right, what I've done is superimposed a very large methane plume, or a composite of multiple methane plumes that we saw over the face of the landfill. So what you'll notice is that we don't see, high concentrations everywhere. And that's because we're not quantifying the total diffuse area. Again, these are just the point sources on the landfill. But what you can see is that we've isolated the plume of where the big point sources are. And when you have it at this high spatial resolution, you can start seeing, like, okay, where are the hot spots? And because of the high spatial resolution, it starts telling you, okay, well, where maybe should I go looking for an issue, if there is an issue. And so that's just one landfill, but we've done many, and there was a big survey back in from 2016 to 2018 that we undertook called the California Methane Survey, where we basically flew our instrument over every piece of infrastructure in the state of California that we thought could potentially be emitting methane. We flew multiple times, detected, tried to, if we saw a plume, we quantified the emission rate and we logged it. And then we said, okay, at the end of the campaign, and we did it multiple times to try to get a sense of variability. And at the end of the campaign, we said, okay, well, what can we say about the point sources in the state of California? And what we basically found was something that some people call a power law distribution or a heavy tail distribution. In this paper, we referred to it as super emitters. I know that that's a very polemic nomenclature, so sometimes we try to steer clear of it. But what we're basically referring to is that there's a small population of emitters that make a disproportionate size of emissions. And so in California, we flew over 436 solid waste facilities. Of those facilities, and most of those, the vast majority of those were landfills. So it was about 300 of those were landfills. Of those 300 landfills, we only detected point sources at 32. It's about 10% that we detected point sources. Everything else was too small, it was too diffuse, our instrument couldn't see it. But those 32 landfills actually made up 41% of all of the emissions in the survey across all sectors. so including oil and gas, livestock. Emissions from those 32 landfills was 41% of all the point sources across all sectors in the state of California. So it had a very outsized contribution to the emissions in the state. But okay, that's kind of the broad picture of what the waste emissions look like in the state of California, at least from the perspective of point sources. What I want to talk about more today is what can you do with this type of imagery at a particular landfill or solid waste processing or organics processing facility, and how can you get insights from this? So it's emission quantification is one thing, but also guiding operations or guiding mitigation is another thing. And so I'm going to show three use cases of the many that we've detected that highlight some of the things you can do. And one of them is quantification of emissions at the active phase or working phase. Another is validation of changes in a landfill. So if a landfill is changing due to construction or infrastructure improvements, can you validate something? And then lastly, I want to talk a little bit about composting and digestion and what you can quantify. So the first is active phase. So here's another landfill in Northern California that we passed multiple times. And in October of 2017, we flew it. And if you look right into so here's on the left is a zoomed out view of the whole landfill. And on the right is if you zoom into the active phase and look at the emissions that we quantified, we see some strong plumes coming from the active phase. And now this is interesting because if you think of traditional ground-based monitoring approaches of the active phase, if you're using FIDs or other technologies, it's very difficult. In fact, usually it doesn't happen where people are scanning on the active phase because it's very dangerous. You have bulldozers, you have active dumping, it's extremely dangerous conditions. You would also maybe think that the active phase wouldn't have a huge amount of methane because this is new trash, right? It hasn't really had time to undergo anaerobic oxidation here and produce methane emissions. But what we're seeing, it's not at every landfill, but we're seeing at multiple landfills, is certainly we are seeing some methane emissions. So this could be due to multiple causes. There could be something about the waste itself that's being deposited that has some sort of methane emissions, or it could be as the working phase, a new working phase is initiated. It's initiated on top of some old trash, and some old trash gets scraped over, and so then that creates a low pressure, so that some methane emissions from old trash might escape. There's multiple reasons, but the thing is that there are some landfills where we are seeing working phase emissions. What was interesting about this landfill in particular is that we came back a year later, and the working phase had migrated. It had moved a little bit farther north within that year, as active or working phases are wont to do. But we went back over and we still saw emissions there. And so again, whether or not this is something about the underlying trash underneath the working phase, or this could be something about the composition of the trash that's entering into the landfill, we don't necessarily have a whole lot of information, but we certainly are seeing that this is a significant contribution. And so we quantified what the total emission of that landfill was of the point sources. It was about 2,000 kilograms an hour. So it was pretty major emissions we saw at this landfill. But we were getting about 10% of the total contribution coming from the working phase alone. So again, not that it's at least for this landfill, the only or the most significant source, but it is a significant source of methane emissions. And it's something that we can now diagnose from aircraft and eventually satellites without having to physically go on to the working phase to make those measurements because it's extremely dangerous. Okay, I want to get to the next use case, which is infrastructure, changes to infrastructure. And so this is a pretty interesting example that we had a lot of success because we worked very closely with the local enforcement agency at Sunshine Canyon landfill in Southern California. I'm sure many of you are well aware of Sunshine Canyon. So in 2016, when we first started flying, we flew over Sunshine Canyon and we saw just these massive methane plumes. And so that's what we have superimposed on the right. That yellow is the methane plume that we saw over Sunshine Canyon. It was permeating over a really large part of the intermediate cover of the landfill. And we contacted the local enforcement agency and Republic and said, hey, look, we have this data, we have this imagery, what's going on? So they were very well aware that they were having issues with methane, but they spent quite a bit of time trying to figure out what was going on with these slopes in particular that was causing so much lost methane to the atmosphere. And what the local enforcement agency came up with was that they found it was an antecedent practice from maybe the decade prior that they believe was really causing this issue. And it comes back to, how do you treat daily cover on the face of a landfill? So, you know, typically at the end of a day of operations at a landfill, you're required to put some daily cover on the landfill, you know, 9 inches or so of soil or some sort of alternative daily cover. Before you start, you know, depositing new waste on the next day of operations, you peel that daily cover off. So what was happening in Sunshine Canyon was that daily cover was not being peeled off at the start of new working days. And so what you were finding was the stratification of, you know, daily cover waste. And what that was leading to, again, according to the local enforcement agency, was some perched leachate sticking up, sitting higher in the trash cell, which meant that there was methane generation occurring not more towards the bottom of the cell, but really higher up near the surface. And this was leading to really unwanted methane emissions, and quite a few more methane emissions coming out of these slopes. So that's what they diagnosed. We showed them the imagery. It showed exactly that they were getting those plumes where they thought there were those problems. So they spent the next year or so investing quite a bit of money, Republic and time, into remediation. And so this included putting, you know, basically two main approaches. One was adding posi shell, which is a, you know, kind of a cement fiber mix, and literally spraying that on top of the on top of these slopes. And the other was closure turf. And so this is basically astroturf, that you know, synthetic grass turf that they put on top of these slopes. And so they put these on top to try to cap the methane emissions, and then they punched a bunch of different wells on top of these faces to really try to suck out as much of that gas as they possibly could. 46 new wells. Here's just and they're taking panoramic shots during the time, so you can really see kind of the progression of the closure turf getting put onto the landfill. So what was interesting is, after they had finished all of that, well, while they were doing it, we were flying our instrument, but even after they finished, we were flying our instrument as well. And what we could see is really a marked reduction in the methane emissions. And so that's the plot I have on the left. Instead of those huge plumes we were seeing, we kind of see a few puffs here and there of methane, but nothing super serious, nothing quite as large. And on the plot on the right, what I have, the red dots represent the amount of mass of methane that we quantified with our airborne instrument. And the blue line represents odor complaints from the surrounding community. So we can see that in the time at the very beginning of when we were flying, we were quantifying a lot of methane mass, and the odor complaints were super high from the community. But as the remediation went on, those odor complaints dropped right off, and so did the quantified methane gas, or the methane gas that we quantified. So it was a way to validate. So it helped so they were already aware of it, but it helped really isolate the places that there were some really large issues, and then we were able to help validate their remediation efforts were having the intended effect. While we're on the case of Sunshine Canyon, you know, there's another example that was really interesting, and that had to do with gabion cubes. So these are, when I say gabion cube, these are basically big blocks of chicken wire wrapped rock. That's what it is. They get a bunch of rocks, stick it in a bunch of chicken wire, and then they stick it at the bottom of a cell before they start placing new trash. The idea of something like a gabion cube is so that it creates an area. So as you start putting lifts of trash there, it's this gabion cubes, because of it has a lower density than the surrounding compacted trash. What this does is it creates a low pressure, so to speak, so that the leachate and the gas can flow more easily into this area, and you would have more effective gas capture if you stick your well right above the cube. This was the idea, and so this was something that they piloted at Sunshine Canyon. So we actually flew over right after they had, put those gabion cubes in and had put in just like 1 or 2 lifts of trash. So it was before they thought they were going to start getting a lot of methane, because not a huge amount of time had transpired since since they had started putting trash onto that new cell, but we flew over and we started seeing plumes almost immediately. So, you know, that's tricky because you're saying, oh, what's all this methane coming from? But it actually here was interesting because it was a proof of concept that the expected activity from these gabion cubes was working, that it was really effective at helping funnel the gas into a low pressure point. So as soon as they saw this, they started applying a vacuum pretty immediately to try to suck that gas out. So again, this is a good opportunity where we're talking about what is the top down telling you and what is a high spatial resolution telling you. It's giving you really direct insights into your operations that if given to somebody who knows a lot about what's happening at the face of the landfill, they can really say, oh, this is having the intended effect, or, oh, this thing looks like it's broken. I can go send someone out and try to fix it. Okay, the last thing I wanted to, well, not the last thing, but the third use case example is for organic diversion practices. So, you know, as I'm sure all of us are aware, state of California has pretty aggressive policy and legislation implemented to reduce the amount of organics that are going to the landfill, with the ultimate effect of reducing greenhouse gases. So, you know, this is great. The question becomes, though, is it having the desired effect? What is the, you know, impact of composting or digestion on our methane budget? These are facilities that aren't really required to report, at least in the same way that landfills are. So if you're trying to assess the effectiveness of a policy and you have a new facility that could potentially be emitting methane emissions and you're not tracking those emissions, is the realization of methane reduction actually happening, or have you just performed some accounting? And so this is the question. And so I'm not saying one way or another that's the case, but the point is, you know, just because you've moved the organic somewhere else doesn't necessarily mean that methane won't be generated. And so you have to really figure out what are potential methane emissions from these facilities. And so this is something that we can also do with this type of instrumentation. Here's just an example. Here's an aerial view of a digestion facility in California with its various different, you know, components of, you know, gas collection. At least what you can see from the aerial view. I mean, they have digesters on the inside, but if you kind of zoom in, these are potential places where you might expect to see a methane emission. If you were to see something, you could see it at maybe a leak in a gas collection bladder, or at a flare if the flare is working wrong, or at a vent, or, you know, at its exhaust and at its bioscrubbers. And so one of the times we flew over during our California Methane Survey, we certainly saw emissions right at the acid scrubbers. So right where the facility was of the methane emissions at the entire waste supply chain so that we can really tell. But that being said, there are certainly opportunities for methane emissions to be seen at digestion facilities, and we should be aware that that's something that certainly could be happening and being released to the atmosphere. The same goes for composting. And so here's just another composting facility in California, various parts along this composting chain. You know how they have the traditional windrows for yard trimmings, but they also have an area with plastic bags where they keep food waste. Then here are the compost piles. So, you know, multiple places, each of those have their own types of operations. We flew over and we definitely saw emissions, mostly from the areas where the organic food waste was being treated and stored, which is no surprise. Again, is this less emissions than what we would see from a landfill if this had gone to a landfill? Maybe it is, but we need to be accounting for these types of things when we think about integrated assessments of greenhouse gas emissions across the waste supply chain. And also this, just as it can help inform landfills, this can help inform the composting facility of saying, okay, well, it looks like we might be having some issues on a certain part of our facility, so maybe we need to turn over these bags a little bit more, or we need to do something else. Okay, so this was, this talk is about California, but I did want to take a little bit more of a zoomed out view. We haven't just restricted to California, and since 2018, we've started going, more and more states across the United States to say, okay, is this heavy-tailed emission or super emitter or point source activity, whatever you want to call it, is this a California issue, or is this something that we see at a lot of facilities? And so what I have plotted on the left are basically outlines of all the places we've flown our airborne instrument. AVIRIS-NG, we also have an identically built one called GAO, so we fly them all over. And so we've gotten multiple states. A lot of these are oil and gas basins. It's not complete coverage, and actually, as of today, we are flying right now. So we're constantly getting more data in other states. On the right is just places where we've identified methane plumes within these flight domains. And so we certainly see, and this includes all sectors. So this includes oil and gas and livestock as well. But we're certainly seeing methane in all of these places. But if we zoom in some other states where we're seeing stuff, here's, for example, a landfill in Louisiana, where we saw really large methane plumes in the spring of 2021 from two different places. We saw it from the landfill face itself on the left, pretty large emission plume, pretty discrete large emission plume. But we also saw it coming from a cold vent at what looks like some sort of gas processing facility right next to the landfill, and it was also a pretty significant emitter. So again, talking about what's the efficiency of a gas capture system, do we lose that if we're venting those emissions, and how much of those emissions are we venting? What's interesting is this is Louisiana, and so when you start looking at other states, you start looking at different climates and different impacts that might come into play. And this actually happens in California as well, but I'll start here with Louisiana. As we came back in the fall of 2021 after Hurricane Ida and went to this same landfill, and here's just the methane plumes that we saw in that landfill. So we had seen a lot previously, but when we came back, the emissions we saw just kind of blew it out of the water. And our working hypothesis is that this landfill was inundated by the hurricane. And so you were really getting some anaerobic conditions, even in the weeks to months afterwards. And so you were getting 10,000 kilograms an hour. This type of emission rate would be larger than anything or at least close to the largest emission in the greenhouse gas reporting program from EPA, one of the largest single point sources in the United States, just from this landfill. But we also see that it wasn't just, again, coming from the face of the landfill, but also from the cold vent. So it was still cold venting at this time, but at a higher emission rate than before. So this tells us something about how do disasters influence emissions. And we actually saw this in California as well. I don't have any slides for it, but one thing that happens are wildfires. Sunshine Canyon landfill. A lot of that landfill burned in previous fires. This also happened, you think of the Frank Bowerman landfill. A lot of it burned. And so if something burns, if the gas capture system is burned for a while and you got to repair it, it's not really the fault of the landfill operators, but that still is a methane emission that's getting released to the atmosphere. So maybe not from a regulatory perspective, but from a carbon cycle perspective and just a general greenhouse gas accounting perspective, those are emissions that we really ought to know about so that we can include them in inventories. Okay, so all of this is leading me more to space, right? The common question, which is a good one, and sometimes criticism that we get with these airborne campaigns is we say, well, airborne campaigns, you can only fly my landfill a couple times a year, right? And that's true. We can't do it this is not a continuous emissions monitoring system. I wish it were. But we cannot do every landfill in California or the state or the world with aircraft and get the type of revisit that we would really need to kind of constrain, an annual emission, which is ultimately what we would want to do for, regulatory reporting and carbon cycle purposes. So it really starts to become, the way you do this is to space. You got to go to space. So how do you do that? And how do you do that the best way possible? And so that's part of what, my affiliation is now at Carbon Mapper is we're a public-private partnership. So, NASA's involved, Planet Labs is involved, University of Arizona is involved, Arizona State University, and in addition to several philanthropic organizations. And the concept behind this system is to create a constellation of satellites that are very similar in performance to these aircraft that I showed in this presentation, that can do routine monitoring of global waste sites with a revisit, initially of maybe a month, but really as time goes on, getting down to weekly. And when we start getting that type of samples, then we can start really asking and ruling out the questions, or at least identifying, what's anomalous, what's a construction emission, or what is something that's persistent, right? That's what you need these long time series for, because oftentimes we might fly over a landfill, we'll talk to an operator and they'll say, well, you flew over the day that there was a bunch of construction. And this could be true. I'm not saying that that's not true. But the question starts to become, well, if we came back tomorrow, would we see it? If we came back in a week, would we see it? If we came back in a month, would we see it? And that's something that's very difficult to do with aircraft. But with satellites, we have that possibility. But it takes a constellation. You can't do it with just one satellite. And so in 2023, Carbon Mapper, we're launching 2 demonstration satellites that will be able to scan the globe. And we imagine for most urban areas and most waste facilities, we'd be able to get something like a 30 to 60 day revisit for each of the landfills. But ultimately, in 2025, we're going to start expanding that constellation, up to as many as 20 satellites. And this will allow us, again, that weekly revisit. And a big thrust of the Carbon Mapper mission is to release this data publicly. So the idea is within 90 days, maybe even sooner, but at least within 90 days, we'll be able to release this data to a data portal so that anybody, industry, regulators, environmental organizations, trade groups, whoever wants it, or just a concerned citizen, would be able to get the data, visualize the plumes, and see the emission rates for any facilities where methane was detected. And here's just some examples when we start trying to bound the question and thinking about it more on a global scale. Is we were able to fly several years ago, do some flights with our airborne instrument in India. And so what I'm showing on the left is a big landfill plume that we quantified at the Purana landfill in India. And then on the right is a plume that we were able to get with an existing satellite called the Prisma satellite, which has some capabilities like Carbon Mapper, but is severely limited in terms of the type of spatial coverage that it can get and the signal to noise it's able to produce. So it's really unable to get a lot of methane emissions, but for really large, strong methane plumes, it still has some sensitivity. So we saw plumes at both of these, I guess landfills, but really these are informal dumping sites in both of these countries. And the types of emissions that we were seeing at these landfills really would blow anything that's happening in America out of the water. These are just massive methane emissions. And this is really important because when we think about IPCC reports or global inventories of how they categorize different methane emission sectors, usually waste is third after livestock, or at least anthropogenic is third after livestock and oil and gas. And it's usually somewhere 15 to 20%. And that could be true, but the data we have for global waste emissions is really poor. We don't even know where all the informal dumps are globally. So when you're trying to create an inventory, how do you quantify something that you don't even know exists? And then for the ones that we do know, lots of these sites would not fall under kind of a land gem or IPCC type of bottom-up model. There's just no management there. There's nothing regular about their operations. So really the top-down approach is, in my opinion, what we're going to need in order to be able to constrain these types of emissions. And so the big question is going to be, is it a bigger contributor or is it not? And we don't know yet. But we won't be able to know that until we actually start observing it. Oftentimes we say, you can't manage what you don't measure, and it certainly applies when we think of in the global context of waste. That certainly is applicable. Okay, so I've kind of left a lot of time here, but I thought it would be good. This would be good to if there's some discussion, I'm happy to take it. But just, as conclusions, airborne monitoring has been a really great precursor to show us what we can do from the waste sector. It allows for this quantification of point sources at particular facilities and allows us to do attribution and emission quantification of these point sources. We've been able to detect landfills at multiple parts of the landfill, the active phase, intermediate, in the gas capture system. We've seen emissions at all of these places, and we've talked to operators and to local enforcement agencies who have done the ground surveys to verify that they had issues, and we were able to validate remediation. Organic diversion is a real thing. In terms of methane, we have seen emissions there, and we need to do the life cycle assessment. I don't think we're prepared yet to say one way or another, but it's hard to say how that's working without those measurements. Finally, it's all about space as we go into the future. Okay, I'll leave it there, and I'll answer any questions. Thanks so much.
Hi, Bhaskar. This is Sarah Head. I have a question.
Sure, yeah. So we'll open it up for questions, and just unmute yourself when you ask a question. Go ahead, Sarah.
Sure. So Daniel, great presentation. Thank you very much. One of the points you made was that the methane emissions weren't reported necessarily from landfills, but one thing that occurs to me is that VOC emissions are reported are regulated by the air districts for landfills and compost areas. And I'm curious if your technology can also detect VOCs. I think if it could, then you would, get a lot more support from air districts to be able to have much better quantification on the VOCs that are coming off of these sources. And, by corollary, then you could also be capturing this methane data. So I'm interested in what your technology can do for that.
Yeah, this is excellent, and yeah, thank you so much for the question. And trying to find the connections between the air quality and climate is certainly what we need to be doing. It is very unfortunate that this technology does not quantify VOCs. Outside of methane, it really just quantifies methane and CO2, and doesn't provide those VOCs, which underpins so much of the enforcement and the regulatory framework. So it's really a great point that's a huge part of that, Brian, and actually is something that we've done quite a bit of research on with at Carbon Mapper, but it's still very much preliminary, where if you do know something about composition of the gas, and you know something about the emission rate that you're getting of methane, you could start saying things, at least through a modeling framework of what you imagine the VOC concentrations to be, right? Because you have an emission rate of methane, and if you have a good certainty, or at least some semblance of an idea of what the gas composition is, and it's going to vary, right, from landfills, or even if you think of other sectors like oil and gas, it'll vary. But people do this, and they do the surveys to try to see what that is. You can start to put together a picture of what a likely VOC emission would be in a place where methane was also observed. So finding those connections, even if it's not through direct measurement, but where we feel like we're on very solid ground to say something about the VOCs, is very important, actually. And we're well aware of, but I appreciate the comment, because there's still a lot of work to be done in that arena.
Yeah, I think that would, really help in terms of, we're doing a lot of work with compost areas in the San Joaquin Valley, and I mean, there's just not good support for the VOC emissions and how much should be offset, and it's a huge problem right now. So I think if we can find the way to tie in some measurements that might be easier than, say, trying to do a source test of a compost area, it's, that's really tough. And so I think these kind of methodologies would really help, spur both kinds of inventories.
Right. Yeah, no, I really appreciate that. That's good to know.
Question?
Yeah, this is Matt.
Matt, hold of Paul. Want to go ahead?
Oh, thank you. Daniel, I'm familiar with SB 1383, which you would know about, is a large massive undertaking to recycle organics and get them out of landfill. But I'm not aware that either Cal Recycle, that's responsible for the law, or the Air Board have picked up on the monitoring of compost and AD facilities for methane releases. Are you working with them in any way? Have they shown interest in your work? Because we're supposed to be achieving a 40% methane reduction by 2030, but if this is unmeasured, how would we know?
Yeah, absolutely. So no, I really appreciate the comment, and I would actually really appreciate if anyone on this call had connections to Cal Recycle for people to speak. We've tried reaching out a few times. I think it's never really quite worked. We do speak a lot with CARB, and they're close collaborators on all of this work, but clearly that's a different agency, and for waste, Cal Recycle's the one. So, but I agree. I mean, this is what we're saying is. I never want this to be misconstrued. Get the organics out of the landfill. Obviously, that's what we want to do. But the point is, this is a system, right? And there's a waste system or supply chain, and there are places where methane can be emitted across that whole supply chain. You haven't really achieved your standards unless you can monitor or understand the emissions at each of those segments, and you can get emissions at each of those segments. So yes. Yeah, I appreciate the comment. Unfortunately, I don't have a close collaborator at Cal Recycle.
Yeah, I think it's a fairly glaring omission at this point in the regulatory framework. So I have pointed this out because I was aware of your work to representatives from Cal Recycle, but what you're telling me is that they, at this state, there does not appear to be a real interaction going to achieve their mandate.
Yeah, but hopefully we'll be able to talk at some point. See if there's a way to leverage this. We're certainly interested.
Thank you.
Go ahead, Matt.
Hi, this is Matt Dunn. I have more of a national type, and maybe a marketing question for you, but on both sides of the environmental spectrum, there's a lot of distrust of E&P, exploration production of oil industry, especially West Texas, New Mexico. There are not many regulators out at West Texas and New Mexico. There's a lot of varying numbers of the production, and if you look at the actual numbers, we're talking 4 to 5 million barrels a day coming out of West Texas and New Mexico. New Mexico's already up to 1 million, which is like twice what California is. So, just doing raw numbers, $100 a barrel, blah, 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 you could easily finance stationary satellite over New Mexico and West Texas if you got people together. And I didn't know whether A, you're approaching that way, or B, there's too much mistrust to even try to go that way.
Yeah, this is an excellent, thank you. This is an excellent point. And yeah, I would be happy. This talk was not about the Permian, right? And we have done, and you may have saw the slides, we have done extensive airborne monitoring over the Permian and quantified emissions there and leakage rates there. And it's, not trivial. And even a day-to-day variability in methane emissions in the Permian Basin is probably higher than all of the state of California's methane inventory. So, if we're talking about, is there a lot of methane being emitted to the atmosphere, and then, where's the interest in, and where's the money to do this? Yeah, these are all parts of the conversations that we're having strategically as we develop Carbon Mapper. I certainly talk almost every day to industry, and so. I won't get into the details of all that. There's a tap dance that we do, but, obviously oil and gas operators are very interested in understanding where they may have leaks in their supply chain, or where it might, where there's expected and unexpected emissions, and what's the magnitude of the unexpected emissions, and what does that mean from a economic perspective, and what does that mean from a regulatory perspective? There's a lot of people very interested in this, and there are a lot of there are a lot of companies that are actually springing up for this as well. And we're a company, but we're releasing all of the data, publicly. So yes, the answer is yes, but it is very complicated on how to actually make this work in a way that is public and transparent and works for all parties.
But your constellation are they like things that just orbit the Earth and take a snapshot a day, or are you talking like stationary?
So these are sun synchronous satellites. So these are not geostationary. They're not pointed at a certain place and just looking at it all day. These go over the Earth over the course of the day. So you have a constellation that's doing that. But each of these satellites, but what we have is we task these satellites to only look at certain parts of the Earth that we think. So when they are crossing over, okay, really prioritize looking at this spot. It's called a target deck. So we're not looking at every square mile of the Earth's surface. We're just looking at the parts of the Earth that we think that there might be methane emissions. And so certainly West Texas, New Mexico is a high priority deck that we are going to throw, most of our, tasking priority onto, in addition to other places. We're certainly well aware of that. So that's, one of the big areas.
Thank you.
Yep.
All right. Anyone else has question? Just unmute yourself.
Namaskar, this is Pierre.
Hi, Pierre. Go ahead.
Hi, Daniel. Thanks for the presentation. My concern is with the accuracy of your estimates. In California, there are an awful lot of reported methane and CO2 emission numbers, both from landfills and the PLTWs. Have you done any comparison with the reported numbers? And some of the reported numbers come from source tests, so they may be more accurate. So have you done any comparison between reported numbers from facilities and the estimates you're coming up with from the mapping, from the projections?
Yeah, this is excellent. Thanks for the question. Yes, short answer is yes. And again, this goes back a little bit to, we are quantifying point sources. We're not quantifying all of the emissions on the landfill, but this is still a significant part of the total landfill emission. So for these 32 facilities where we detected something, we found on average our emission estimates were several factors higher than what was reported to the CARB inventories and to the EPA inventories. So it suggests an overestimate. That said, what we did for the California surveys is for many of these landfills, we actually contracted out with another private company that does emission quantification called Scientific Aviation, where it's a totally different approach, where they do mass balance and they fly concentric circles around a landfill and quantify the upwind methane concentration and the downwind and the wind speed to come up with emission rates. Our estimates were very close to theirs. Theirs were usually a little bit higher than ours because they quantify the full total flux from the landfill and we just do the point sources. So we did do several of those to give us some confidence that we were not, totally out of the ballpark in terms of what we were quantifying for our validation. We certainly are doing more of those, and actually, as we speak, we're coordinating lots of measurements on the southern and eastern United States, where we're flying right now with many industry operators to make sure that we're refining these emission estimates. And the point is that until we have more of it will never be a continuous emissions monitoring system, but we have something that's a little bit more continuous, or at least where we're getting sampling on weekly to maybe bi-weekly or worse, monthly scales. It's very difficult to average a few snapshots that we see from a landfill and compare it to an inventory, an annual emission estimate inventory. So we do the best we can to do the validation for the snapshots themselves using independent methods, and we're going to continue to do that. But ultimately, once we get the sampling cadence up, we can start really looking at comparing to inventories to see, okay, on an annual scale, is this something that is still showing to be several factors higher than a bottom-up inventory?
Fair enough, thanks. The second question has to do with other pollutants. I know for landfills, vinyl chloride is of particular interest, and for POTWs, ammonia is of particular interest. Have you looked at this technology and whether it can work for other pollutants?
Yeah, so as of now, really, it's methane and CO2. Unfortunately, is all we can do. We can't get these other ones. But ammonia, you can do through other remote sensing techniques, just not this instrument. And so there are thermal satellites, for example. So the EASI or CRIS satellites, and there's others, kind of coming down the pipeline that do ammonia quantification. And so then this starts to become very interesting from a correlation perspective of what we see from the methane and the ammonia. And getting back to a previous question, if we have good measurements and in certain places, and we've developed, methane ammonia correlations or correlations with other tracers, and we know something about a methane emission rate, we could potentially, again, the devil's in the details, but you could potentially start using the methane emissions as proxy. But you'd have to do the right validation and compositional studies in order to have confidence in that.
Great.
Fair enough. Thank you.
Thanks, Pierre. We probably have time for one more question if anybody has any. No. Seeing none. Daniel, I'll go back to Sarah's comment, on the VOC, not just for the landfills and composting facility, but that could have applications with other facilities, like large refineries or something if you want to monitor them. Yes. But I had the same question that Sarah had. Seeing no other hand raised, Bernadette, I think you can close out at this point.
Yeah, well, thank you so much. This is great, and this is a great discussion as well. So I really appreciate the time and the conversation.
Thanks, Daniel. It was a very, very good presentation. I think there will be a lot of opportunities in the future. I know on a professional level, I get asked frequently, I work for an instrument company, about they're interested in compost. And I'll ask, well, what do you want to know specifically? Because it is complex. And every once in a while, I'll get like one chemical that they're interested in. And I'll be like, well, that's going to be difficult. If somebody could come up with a list, because a PID can do a lot of different measurements for VOCs. But what specifically do you want and how do you want to correlate it? Then instrument companies can then look to design. But right now, it's, I think, too open-ended for instrument companies to say, yeah, we want to design this specific instrument. So it'll be interesting going into the future. But we definitely wanted to thank you for presenting, to welcome everyone to join West Coast Section AWMA, because we would be interested in that. Somebody trying to ask a question? Okay, somebody just joined. So we would like to welcome everybody to join, to get involved with West Coast Section. We do have additional presentations in climate coming up. We have two in particular. One is coming up on May 26th. It's addressing climate change, COP to COP negotiations in progress. And we have a second one coming up on Swirling Currents, a plastic journey from macro to micro and back. Those are both webinars that are from 12 to 1. They're on our website. And also AWMA does have their ACE the end of June 26th to 30th in San Francisco at the Hyatt for those to attend. So I'd like to thank everyone for joining, and we look forward to seeing you at another one of our talks.
Thank you.
Thank you all. Thank you.